Sir, I'd like a general question.
Okay.
Sir, like, how do you solve like a Schrodinger's wave equation? Like, how does it, like, what does it mean to solve?
Mm, what are you really asking?
Like, sir,
What does
Schrodinger.
it mean to solve the equation?
Yes, sir. Like, we get like the wave function, right? Like,
What do you understand by Schrödinger's equation so far? Let's go there first.
so it basically tells us about the like the information about like the electron. I mean, like,
Okay, so let's start off with the analogy first. So you were cooped up in a particular place during your COVID time.
hmm,
Okay, so basically, look at your entire duration of your COVID time with your house in a map form. You are a dot in that house. Okay,
hmm,
now I want you to think of your entire COVID time. You are the dot which is present in the house. So if you're going to be sitting in your spot here, you're going to be sitting in that spot. You'll be seeing a God's eye view. The map will be basically like a 2D map which you're seeing.
hmm.
Now, your entire COVID period, bring it down into a video of 2 minutes, represented like that. What will you be? You'll be a dot which is like moving constantly here and there,
Hmm.
right?
Yeah.
Now, I want you to try to understand that mathematically. What are you? You're a constantly moving object,
Hmm.
constantly moving dot. The way to depict you is like some kind of a wave,
Hmm.
because I don't know where you are stopping, etc. I can't stop you at a particular instant.
Yeah.
So I'm going to be looking at you as a wave right now. So when I look at you as a wave, there will be some equation associated with you.
Yeah.
So how do I study you as a wave now?
Wait, sir. You said there'd be a equation associated with. What do you mean?
Associated with that wave, which is moving constantly. It is a point which is moving constantly, correct?
Yeah. Yes, sir.
I can depict that by some equation.
Like the path it follows, like that.
Whatever, I don't care what it is. Mathematically, I can depict it if I set of parameters, right?
Yeah.
Like for instance, in your house, if I give you a house set of dimensions,
Hmm.
I can then start representing you with a point over there as a particular point which is there in the 2D. I can then represent you as a wave, correct or not?
Yeah.
As some mathematical equation, I don't care what equation, but some equation is applicable. Yes,
Hmm.
that equation is your wave equation. That is the equation which is you as a wave. That is you as a matter wave.
Gives
Now, if I
location.
want to study you as a matter wave inside this unknown space called your house, for me, it's an unknown space, correct?
Hmm.
I will break down your house into pieces.
Yeah.
And then I will study your wave like nature or that equation which represents you in each of those places.
Hmm.
That is literally what we are doing when it comes to the atom and when it comes to the electron inside the atom. So, what is the Schrodinger's wave equation? Schrodinger's equation basically talks about electron as a wave. What does it mean when I say we're going to be taking the electron as a wave here? The electron is the object which we cannot isolate and say it is present here. It is not a particle anymore. I cannot
Hmm.
say where the electron is. I can never find the electron. It is a constantly moving object.
Hmm.
So when it is a constantly moving object, I only know the path it is basically or where all it has been done because of the effects it has left on the field which I can sense. I can sense the electric field.
Yeah.
I can sense the magnetic field. So based on those fields and the effects the electron leaves, I can sense that it was there, or it should have been there, or it probably was there, something of that sort. I cannot tell where the electron is ever going to be. So I'm going to consider the electron as a pure wave now. So the electron is a wave. We have what is called as a very famous thing called as standing waves in physics.
Hmm.
let's quickly talk about what is a standing wave. So if I'm going to be having, say, this is a wall here. Let's say I'm attaching a string on this wall here, and I make waves on it. That is called a standing wave. What is the speciality of a standing wave? If the thread is present over here and I'm making waves on it, the idea there is very simple. In that, I'm going to be having the wave is going to be bound within the space of the thread.
Okay.
Right. So basically, I'm going to be having my hand over here as a thing here. If I'm having a string here, I'll make a wave. The wave will travel. It will hit this wall. It will rebound back, opposite angle, phase change के साथ, and it will be present in the same wave. So this direction wave and the opposite direction wave are all in that same string only. So because the wave which is moving this way is also bounding back, it will both interfere with itself constructively and destructively.
Yes.
Creating your nodes and antinodes.
Yeah.
You've learned about that, correct?
Yes. Yeah.
This is a typical standing wave. But this is a typical standing wave in one dimension.
Sir, but then won't all...
Let's not go there. You understand till what I've talked over here, yes?
Yes. Yeah.
So this is a typical standing wave in one dimension. Now, standing waves in one dimension have a very famous equation in physics called the standing wave equation, which is a double differential equation which applies to all standing waves in one dimension. When I say applies, I mean it works at all for all standing waves in one dimension. That equation is going to be something like this. If I take psi, or rather, let's say I'm talking about y is equal to f of x as my standing wave in one dimension. Okay, the equation of the wave is y equal to f of x. X is my amplitude.
Yeah.
In one dimension. Y is my equation of the wave itself. Okay, yeah. What is going to be happening now is this y equal to f of x over here, I'm now going to be double differentiating it. It will become d square y by dx square. Differentiating it, of course, with respect to the only variable I have, x. This is going to be equal to minus 4 pi squared by lambda squared into f of x. This is called as your standing wave equation. This is a double differential equation, as you can quite clearly see, which is going to be applicable for all standing waves.
Okay.
You can test it. Please do so. The physics testing, I'm not going to be going there. You sit and test it out. The physics equation called standing wave equation, it applies for all standing waves in one dimension. Schrödinger now mimicked the same model. What was the mimicking he did? He took that the wall is the same as your, what to say, nucleus. The electron is the wave itself. And it is bound inside the space called the atom. You understand the idea here? So I'm going to be having a three-dimensional space now, where I'm having a wall present in the center. That wall is extremely heavy, and you're going to be having a string which is going to be attached over there, which is obviously going to be present as a wave now. That wave is my electron itself. So in this case here, I had a wall, I had a thread attached, I had myself making waves on the thread, correct? So what was the force holding the thread to the wall in this standing wave which we talked about? This was tension force.
Tension.
So I had tension force here.
Here we have...
Instead of tension force, what will I be having? Electrostatic.
Yeah, Coulombic.
Coulombic. And here it was one dimension in the first place over here. Here the electron is going to be in a three-dimensional space over there. So 3 dimensions. So I will be extrapolating this equation. to 3D. When you extrapolate that equation to 3D, the equation becomes, instead of d square, it will become dou square. And in this case here, instead of writing it as y equal to f of x, I'll be writing it as a new equation over here. Psi is equal to f of x comma y comma z.
Yeah.
Okay. So I'll be having dou square psi divided by dou x squared plus dou square psi divided by dou y squared plus dou square psi divided by dou z squared. This is my triple double differential for the entire thing. This entire nonsense, I'm going to call it as del squared psi now. Capital del squared psi.
Yeah.
This is supposed to be equal to minus 4 pi squared by lambda squared into f of x. But instead of f of x, what do I have here?
Psi.
I have psi.
Okay. Yeah.
So far clear?
Yes, sir.
So now this will basically work out as del square psi is equal to minus 4 pi squared by lambda squared. This is going to be the electron itself as a wave now, matter wave.
Yeah.
So de Broglie's nonsense should apply.
Yeah.
So lambda squared should become lambda, which is equal to h by mv squared.
H by mv squared, yes.
So it works out as h by v whole square multiplied by psi. So I'll be having del square psi working out as minus 4 pi squared by h squared into m square v square. So I can write as m into mv squared.
Yes, sir. Energy.
Correct? mv squared is what?
Kinetic energy.
Kinetic energy. But is
Two
it
into
kinetic
kinetic
energy?
energy.
Twice kinetic energy.
2 into kinetic energy.
2 times kinetic energy. So this works out as minus 8 pi square m by h squared into kinetic energy into psi. Kinetic energy is what? Total energy minus potential energy.
Yes, sir.
So I'll write this as del square psi now is equal to minus 8 pi square m by h squared into E minus V. E is my total energy, V is my potential energy multiplied by psi. This is your final form of Schrödinger's equation.
Yeah. Okay.
You understand the idea here? So Schrödinger's equation is nothing but the standing wave equation extrapolated to 3 dimensions. So what the hell did he solve for? He solved for psi of x comma y comma z.
But then why can, like, they say that we can only solve for like s orbital or something like that.
No. Schrödinger has solved for all of the individual pieces. What is an orbital? What did I describe to you? What is the thought experiment which you were told to think along as the case study here? You are the wave.
Yeah. Yes.
And your entire COVID period is basically shot into a 2-minute time span. You are the wave. If I want to study this wave, it is too complicated, correct? The equation is too complicated. I can't study it in a proper manner because the equation is different in different parts.
Yeah.
Right? So in your room, you are going to be in a particular place in a particular manner only. In the dining table, you're not going to be lying down. You're not going to be pissing on the dining table. You're going to be only sitting there or you're going to be standing next to it. Right? There are only certain ways in which the way which is you will be behaving there. Yes or no?
Yes, sir.
So the idea here is you're going to be looking at this particular wave in a way in which you break down the space inside which you're studying. The atom now is your entire house.
Yeah.
You are bound in the space called your house.
Yes.
By whatever attractive force, I don't give a shit there. But the reality is you're bound in that space. You behave differently in different rooms. And in different rooms, in different parts, you behave differently. At different times of the day, you will behave differently.
Yeah.
Right?
Yeah.
That's basically what we're doing here. So what did Schrödinger do? When you talk about a particular subshell or a particular orbital, what does that mean? A particular location inside the space called the atom, you're trying to find the equation of the electron, how it is going to be behaving.
Okay. So,
You understand the idea?
Yes, sir. Yeah.
What is the problem there? The problem is this. When you
Have
are
to-
one individual in one building, it is easier to basically identify what your behavior is going to be. You can predict it reasonably well. But if there are two individuals, what happens? They will interact with each other.
Yes.
Predictions become much more complicated.
Yeah, yeah, yeah.
That is why we can't predict when there is more than one electron.
Okay.
You understand the principle over here? So we can
Yes.
basically do Schrodinger's also for only one electron species. It is solved only for single electron species. What does solved mean? He found out the equation, that's all. He doesn't understand shit beyond that. Mathematically, what is the equation? He knows. So if there is one person in a prison-like environment called an atom, a big building, massive prison called the atom, how will they behave inside that space called the atom? How is their behavior? How do you study it? You basically break down the space called the atom into pieces, into different rooms, and in those different rooms into different locations.
Yeah.
And in each room you study, in each location you study, what is going to be the mathematical equation for that species called the electron.
Okay.
The mathematical equation by itself gives no meaning. But if you take psi squared of that mathematical equation and you study that, that has some physical meaning. The physical meaning is going to be what is the probability of finding the electron in that spot.
Okay. So then for a standing wave, if you square that f of x, will that also give you a probability
I have
density?
no idea about that.
Okay.
Do not assume that I know the physics beyond a point. I know the physics which is going to be connecting here sufficiently. I do not know beyond that level there. You understand how Schrödinger's works now?
So why exactly does the psi square give you a probability density?
No idea.
Okay. Okay.
Now, how is it studied? Schrödinger basically derived psi of x comma y comma z. The equations, we have no idea how to use them. They're very complicated. So he solved it and he got the Nobel Prize. The next shit came to understanding them and how to meaningfully pass down the knowledge. So that is where Hamilton comes in. I'm assuming you have learned about something called the Hamiltonian operator.
Yes. Yeah.
So what this bugger did was he converted this psi of x comma y comma z, which Schrödinger solved for, which was in Cartesian coordinates, into what is more easier to understand for us, which is spherical polar coordinates.
Yeah.
Why is this easier to understand for us? Because if you write the psi of x comma y comma z in this form of psi of r comma theta comma phi, you can break this down into a new manner here. Psi of r comma theta comma phi can now be written as r of r multiplied by a of theta comma phi. Basically, you can write this one big equation called the electron now into two separate parts. One which is going to be an r of r part, another which is going to be an a of theta comma phi part.
So factorizing the thing.
Yes, you are factorizing it, exactly. So this is called as a radial part.
Oh, that's why. Oh, okay.
And this is called the angular part.
Now,
what does the radial part tell you? The radial part is going to be the mathematical part of the equation, which is going to be doing, or which is going to be involving anything and everything from, which is going to be talking about only one variable, the distance of electron from the nucleus. Whereas the angular, so this is going to be covering distance of electron from nucleus.
Okay.
What should the angular then cover?
The angular position.
What does that mean? Direction.
Direction, exactly. Yeah. It's like
direction of electron from nucleus. Now, obviously, even the r of r and a of theta comma phi are massive equations by themselves. So we cannot remember those equations. What can we remember out of them?
Can be broken down.
So we remember the graph for R of R. So when you are plotting, say, psi versus R or psi squared versus R, you know these graphs,
Yeah, psi
right?
square 4 pi. Yeah,
And you know also psi square, or the not really psi squared, you also know
4 pi r
4
square.
pi R square psi square
Yeah.
versus R. You know these three graphs, correct?
Yes, sir.
What are you really plotting there? You are plotting, instead of psi, you are not plotting psi, you are plotting R of R versus R.
Okay, so we're not. Okay.
You're not plotting the entire thing, you're
Yeah.
only plotting the radial component.
Hmm.
Same way, when you're plotting psi squared, you're actually plotting capital R squared of R versus R.
Maybe that's why. Okay.
And the graphs, the shapes are all you remember,
Yeah, that's
right?
yeah. Yes, sir.
Because those shapes tell you where you're going to be having a node and not a node, where you're going to be having a peak, etc. etc.
Hmm.
Basically, this is all you are learning. 4 pi R squared psi square. Now, what are you really doing? You're plotting 4 pi R squared into capital R squared.
Yeah.
Of R.
Yeah.
So, what this gives you is, when you're multiplying by 4 pi R squared, that means you're taking
Yeah.
the entire sphere of points on the surface over there of the sphere, all of those points.
Yes.
4 pi R square stands for what? Surface area
Hmm. The shell.
of a shell, or of the sphere of radius small r.
Hmm. Yeah.
So what you're calculating there is the total probability density or
That
total
enclosed
chance
inside.
of finding an electron at a distance r from the nucleus.
Okay.
This r squared of r, you're going to be calculating not the total chance here. You're calculating here the chance of finding an electron at that particular distance r from the nucleus. This is going to be average. This is total.
Average. Average total.
This is average across all directions.
Hmm. Total across all directions.
Yes. Total across all directions.
Yeah. Okay. Hmm. Hmm.
You also learn a squared of theta comma phi. The graphs for these. What do you think these are? I'm telling you, you know this. What are these? You know them
Angular
by a
lines.
different name though.
Sir?
You know them by a different name.
Um, so we, oh,
The plots of a square of theta comma phi are basically the different shapes of the orbitals. S orbital is a spherical shit. P is going to be this dumbbell. How do you get that shit? What does that mean? That is basically plots of a square comma of theta comma phi.
oh, okay. Yeah. Yes, sir.
You understand the idea?
Yeah.
So you learn two types of graphs actually. One is radial graphs, another is angular graphs. We don't call it that way though, but that's what you're learning. Because
So
we
then if
can't
you,
remember the exact mathematical functions. They're too complicated. What we know is we can remember the easier part of the solution. That is what we are memorizing. That
so
is
if you
what.
have, if you have R of R and A of theta and all this, why can't you get psi?
You tell me, is it going to be still that simple?
I mean, it won't be, but then we can do it, right?
Let me ask you a very simple question.
I
Draw
mean,
the shape of 3s orbital. Shape of the 3s orbital. How will it be?
spherical.
Spherical, yes.
Yeah.
No doubt about that.
But
But
then there'll be gaps inside, and then
you're getting the
yeah.
point now, no? So 1s is going to be this guy. Then there will
Then
be
a
a gap
P
between,
as a 2.
and then you'll have your 2s, and so on and so forth. I think you start getting the basic problem over here, which will be coming up.
Hmm.
Right. So the
Sir,
gaps, what are those gaps? Those are the radial nodes,
radial nodes. Yeah.
right?
Hmm.
So just for the 3s, it is that complicated.
Hmm. P and all that bit.
Yes. You understand why we break them down into pieces, and because the individual data, when you keep collecting it together, now it gets too complicated.
Hmm.
We cannot simply understand shit out of it. So we break it down. We break it down and we learn it.
Okay.
You understand the idea here?
Yes, sir. Yeah.
Okay.